welcome to the fourth day of the summer school. My name is Adria. I am a first-year PhD student here at ILMO, and I will be the chair in the first session. So it is my great pleasure to introduce you to today's lecturer, Professor Fernandez-Corbaton from the Karlsruhe Institute of Technology. Professor Corbaton is a worldwide recognized expert in the theory of electromagnetic scatters. So he's one of the pioneers in the applications of symmetry and conservation laws for the rational design of novel nanophotonic devices, and the author of several highly relevant works in the field of chiral light-matter interactions, which is actually now one of the hottest topics. Among his many investigations, he has recently come up with beautiful expressions that allow the calculation of multiple moments of a scatter of arbitrary size and shape, making clear links between the different approaches that were used for this purpose in prior research. I believe he will discuss the formalities with us today in detail, so with no further delay, Professor Corbaton, we are looking forward to your lecture. Okay, please, whenever you're ready.
Thank you very much, Adria, for this very kind introduction. Good morning, everybody. You guys can see my slides? Okay. All right. So, yes, as Adria was saying, today I'm going to give two lectures on this topic, exact multipolar moments of localized sources. First, I thank you very much, the organizers, for giving me this this opportunity to present in the summer school. I really appreciate it. I'm very glad to be here, and I hope that you can enjoy my my lectures. Okay, so what we have, we're going to start with just some cartoon. Okay, so we have here is a spherical volume where I have some sources. So these sources are J, RT, so the current density that depends on position and time. And as you know, these sources will produce an electromagnetic field, E and H, outside. And our task is to understand this, electromagnetic field from outside the sources using the multipolar decomposition of the sources. The typical route, so I'm going to show you now typical methodology. You've seen a few of them already in previous lectures. This is one that Jackson did in his book. This is in chapter 9. So what one does is takes the JRT and does a first Fourier transform to go to omega. Okay, so now we have here these objects, J omega of R, which are the monochromatic components of the spatial and time varying current. And then, as Jackson explains, if you consider each of them separately, right? So we first had the whole JRT, and now we have already some decomposition. But because Maxwell's equations are linear, if you consider them separately, you can show that outside the source, you can compute the vector potential in this way. Okay. Okay, so it's just an integral over this. You might recognize this from other lectures. This is the scalar Green's tensor. And if you do some approximations now, you've seen some of them in Professor Euclid's lectures, including that the size of the source, so this R here is basically the characteristic size of the source. It's smaller than the wave, much smaller than the wavelengths, and then the point of observation is much bigger than everything else. Then you can do some expansion, expansion of the exponentials, and you get that this term here gets a piece on the left, and also this summation. Okay, this sum here, which runs with index n, starting at 0, and then you get these integrals over there. And then Jackson goes on through the chapter, starts with n equals 0, and he gets what has been called the electric dipole. So this proportional to this integral. I mean, easy to see, n equals 0 here. And if you go to n equal 1, you will get what it's been typically known as the magnetic dipole, R cross J. And in n equal 1, you also get the electric quadrupole. Okay. Then you go further, n equal 2, and Jackson will get you the magnetic quadrupole, and he will mention the electric octopole. And if you actually do it carefully, you will also recover here a toroidal dipole. Okay. We will see some different expressions that some of them look like this one, some of them are quite different, which instead of these approximations with sizes, the expressions will be exact. I first want to call your attention onto one thing. This kind of expansion is mixing the multiple orders, right? So for n equals 0, I get just one kind of order, but for n equals 1 I already have two things. And n equals 3 will give me 2 or 3 things, and so on. We'll see why this happens. Just as an introduction, as we will see, the multiple moments of the current completely determine the electromagnetic field outside the source. And you can see this by, first, for the far field, you have expressions like this, you've seen them before. But you can also use other kinds of expressions. This is also in Jackson, where the expansion works also not only on the far field, but also in other zones. Maybe you don't know what these N and M are, but we will talk about them quite a bit. Maybe you know them. So these are radiating solutions of Maxwell's equations, and they are characterized by having a well-defined frequency, which is omega, angular momentum, which is characterized by these two indexes, J and M. We will see what they are, and parity. So let's think where these currents, okay, we have the very beginning currents. So in nanophotonics, what is the typical setting into which these currents appear? And the typical setting is that you have an object, you illuminate it with an incoming beam, and then the object and the beam interact for a little while in this gray area. And then later we have again the object and the beam, but they don't interact anymore. And now there is an extra piece, scattered field has been produced. And you can understand this by thinking that the incoming field induces this polarization currents in the object. Okay, so the JRT is now inside this green shade. And typically, in nano-optics, in many cases, what we do is we have a Maxwell solver. It could be COMSOL, it could be JCM or something else, or maybe we know the solution analytically because this is a sphere. In any case, this gives us the total electric field inside. And then you can compute this current by something like this, by a formula that gets you now the J omega of R, and then you could do the multipolar decomposition of J. These multipolar decompositions are, I think I don't exaggerate if I say that this is one of the most important tools in nano-optics. And it's used in both the analysis of what happens with the radiation and the design, where you try to, let's say, cause some interference between different multipoles or get a single one or something like that. I'm going to just mention that it's also crucial, this multipolar decomposition, in many other areas of physics and chemistry. Okay, this is an important tool pretty much in all areas that deal with light-matter interaction. And it includes, for example, the radiation of celestial bodies at spatial scales that are really much bigger than our nano-optics scales, but also at much smaller scales like nuclear, atomic, and molecular transitions. Let me just spend this slide talking about the transitions, because maybe you've heard some of this language before. So the idea is that you have two-level system, and now it's excited, it's in state E2, and now it's going to decay, it's going to relax, and it's going to produce a photon. Okay, and this photon will have a frequency that is exactly the difference between these two energies. In here, the currents that you can think that they are producing this field are called transition currents, and you can roughly think about them as charges that are moving from the initial state to the final state. And in reality, those charges are due to the electronic wave functions, but you can also think about it a bit more classically, let's say. And not only does this photon have a very definite frequency because of this difference, but you might have heard that, for example, atomic levels have well-defined angular momenta. So the angular momentums from level 2 and level 1 will be different, most likely. Or maybe they're the same, but they change in some other ways. And they also have definite parity. So the photon that is allowed to be produced is very well determined, but something that is called the selection rules. And these selection rules, when there is some transition, okay, they tell you, for example, the angular momentum values that are allowed, in this case, 1, so this is dipolar. And then you can also know, by analyzing the electronic orbitals, whether there can be a parity change or not. And depending on that, the photon will be an electric dipole emission or a magnetic dipole emission. So besides the typical examples that you're mostly used to about nanostructures, my point in this first slide was that these are actually very useful decompositions in many other kinds of physics. Okay, getting to the lecture, I will show you a way to derive the multipoles in momentum space, or in wave vector space, or if you want to call it in Fourier space, or in the decomposition of plane waves. And we will talk about parts of the source that produce EM field, electromagnetic fields, and parts of the source that do not. We'll go through these expressions, and we'll see their long wave approximations, giving the correct expression that you're familiar with. And hopefully we can cover this by lecture 1. In lecture 2, we'll talk about toroidal multipoles, something probably new to you, Helicity multipoles, and some other topics, which I'm not sure we're going to be able to cover them all, but otherwise I will just pick and choose which one I tell you about. I think there will be time for all of it. Every now and then, I will ask you a question, and then you will go into the surveys of the app or in the web interface, and you will see that there are 6 questions, and the questions will appear on the screen with a slide, and then I'll give you some time to answer them. And at that point also, after you answer the questions and I look at the results and I make sure that you're kind of following, then I'll also try to answer the questions that you've written up to that point. So
sorry, small interruption. I will just remind the students that to see the questions of Professor Corbaton, you need to go to the section of tests and surveys, not the question section. Tests and surveys.
Tests and surveys. Thank you a lot. Thanks a lot, Mr. Chairman, Adrian. By the way, I'm going to stop my video because I don't think you need the information that this provides to you. Now, if you want to, so the material I'm going to talk about is basically contained in these 4 papers. Okay, they will be appearing also during the slides and also with other papers from other people. And let's go back to the start. So we have our current, and it's confined, and it's producing some electromagnetic field outside. So instead of stopping at this one Fourier transform, what we're going to do is to do one more. Okay, we'll take this one here, and we'll decompose it into the spatial Fourier transform with the integral in momentum space. You can think of this as the wave vector as well, okay, K. I like P because it's more the typical letter that is used for momentum in physics. So in what we will do is, so the JRT is decomposed with this 4-dimensional Fourier transform. And now So this is just the Fourier that goes from TR to omega p, omega being the frequency, p being the momentum. So instead of this JRT or J omega R, what we will use in the lecture is this J omega of p. Okay, so far I've done nothing special, it's just one more decomposition. This is all unitary transformations, nothing changes. And is because of the linearity of Maxwell's equations, is basically the same thing of solving this, solving for this, then solving for this, and then summing. Okay. Now, there is an important result that we'll use right away. And this result is from 1974. This is Devaney and Emil Wolf. And what they show is something quite interesting. Okay, so they said the following. They were using this J omega of p, and they said that at all the points, okay, outside that sphere, the electromagnetic fields of frequency omega are determined solely, so that's the key word, by source components J omega of p that meet this condition. Okay, modulus of p equals omega over c, or if you square it, px squared plus py squared plus pc squared equals omega divided by c squared, c being the speed of light. So this is what you know as the dispersion relations. The interesting thing is that, of course, in here, there are other components that don't meet this. But what these guys are saying is that, okay, you don't have to care about all those other components if what you're worried about is the frequency omega electromagnetic fields outside the source. So this problem in TR space that looks like this, if you go to the energy momentum space, you probably know that energy is the frequency. Then it's changed to something that is like a spherical shell with radius omega over c. Okay, and this, if you imagine that the coordinates here are px, py, pz, and I give you j omega of p, you can throw away everything except what is on the shell. Now, I've been talking about a sphere, and it is should be said that the proof in reference form does only apply to spherical source region. Okay, so then even though this is already a strong result, one could ask, okay, what happens if I have some kind of ellipsoidal region like that? Okay, well, one solution or one possibility is to say, okay, you will just draw a sphere that encloses the whole ellipsoid, and then I will be sure that their result, theorem from Devaney and Wolf, applies outside the sphere. Of course, then with this region that now I'm pointing at, then there will be an ambiguity here. What happens here? Okay, this is not inside the source, but also is not outside the sphere. The good thing is that you can actually extend the result from Devaney and Wolf to regions D of very general shape. Okay, now D is some volumetric region, and you can actually conclude that at all points R outside D, the same thing. Okay, the electromagnetic fields of frequency omega are determined solely by source components j omega of p with in that momentum shell. I'm going to talk about this as being the momentum shell, and out of the shell would mean that when there is a non-equal here. How do you do this proof? It's actually quite straightforward. So you use a result from the original paper from 1974 that says that the far field only depends on the on-shell components. Okay, obviously, if it's the far field would be outside the sphere, and that has to be true. Then you use a theorem in a book, which is actually quite interesting book. It's quite mathematical, but it has a lot of insights on electromagnetic scattering. And this theorem here says that the EM field outside D is uniquely determined by the far field. Okay, and then of course by adding 1 and 2, you get 3. So if the EM field outside D is only determined by the far field, and the far field only depends on the on-shell components, it follows that the EM field outside D only depends on the on-shell components. So if you know the on-shell components, you can determine also the field in this region. Okay, I'll keep drawing spheres to make it simple, but so that you can keep this in mind. So see, now we've done something already that is non-trivial. Here I have all the omega p components. Okay, I did this Fourier transform at the beginning, and okay, I have all these omega p components. Now I know that I can throw away, or let's say I can ignore some of them. So my attempt to draw this is now some of these guys become feeble, so become lighter. So I want to represent that they don't radiate outside. They don't produce fields outside. So we only have to worry about this shell, okay? Just to make it clear here, okay? Omega is fixed because of the it's a monochromatic component, and it's fixed by the fact that I choose one of these exponentials, and then I have to I can actually select the p that is basically p hat, so a direction vector, times omega over c. Okay, so that's the momentum shell. So we will focus on this momentum shell components of j omega, and I will call them by this notation, okay? Some j circle here, p hat, because it depends only on omega and p hat now. And this is the first question for you. Now, if you go to the survey and question 1, let me do it as myself so I see what you are able to see. Oh, it's already there, so nice with the slide. So I'll read the question. Consider an electromagnetic current density distribution, JRT, radiating electromagnetic fields in vacuum. Assume that you can measure the electromagnetic fields with infinite precision in the far field region. And your job is to choose from which of the following statements is correct. 1, you can use the measurements to recover JRT. 2, you cannot recover JRT because the near field information is missing. And 3, both of the previous statements are wrong. So Andrea, I think we'll give the participants like a couple of minutes, 2-3 minutes. And then later we can, if there is any questions that have been written while I'm talking, maybe we can address them. Are there any questions? No, I see a question that's probably not from my lectures.
Yes, right now there are no questions.
Okay, good. So in a couple of minutes, I will, maybe less. I have to take into account that there is some 30-second delay apparently possible. So I don't want to finish the survey too quickly. When I answer the question, I will be the last one, and I will be able to see how you guys did. So we will also talk about the answers. I will explain briefly, not just giving you the right answer.
Dear students, I want to remind you that you should answer in the app, not in the Zoom. In the app, tests and surveys, you will find question 1 of Professor Corbaton.
Okay. I hope there was enough time. I'm going to answer and finish, and I will see the results. Okay. So I don't know how many people replied. I don't know if I can know that. But the results that I see so far are that 73% of you answered 1, 8% of you answered 2, and 19% of you answered 3. And the correct answer is 3. Because, all right, let's say for those of you who answered one, you can use the measurement to recover JRT, okay? I gave you an infinite precision to measure the far field. The problem is, I'll give you an infinite precision to measure the far field. This is fine. So you get this HRT and the far field perfectly, but I spent a couple of slides saying that only not all the J omega of P components are going to produce a field outside, which means that, okay, because of this result, which means that if I give you the far field, the only thing that I'm giving you really is the on-shell components here in this momentum shell, and you will not know all the other J omega of P components, so where this condition is not met. And actually, this is a famous problem in inverse scattering. The inverse scattering problem is ill-defined in the sense that because of this, the field only depends on the on-shell components, you cannot determine uniquely the radiating current. Okay. Then two, you cannot recover JRT because the near field information is missing. That's also wrong, because as we said before in this slide, just with the far field, you can get the near field. Okay. You have to maybe use it smartly, but you can, in principle, all the information is there. And then the question was 3. Their answer was 3. Both of these are wrong. I'm actually not very surprised to see that many of you answer 1. But this is something that you will, hopefully by the end of the lecture, you would never answer 1 to this question ever again. All right, let's continue unless there is questions. Adrian?
No, right now everything is empty, so it's clear.
All right, so let's focus on that. Okay, so we have a shell in momentum space with radius omega over c. Okay, and what we do, it's something that it's easily understood from algebra. I will find a basis for the functions that are defined here, and I will expand my J circle here, J on the shell, with that basis. And those bases will be related to multipolar functions, and for now I'm calling them Z, X, and omega, right? And just to give you a sense of what they look like, omega basically, so if you take a piece here and make a zoom, omega is going to be something that is always pointing along the direction of the momentum, okay? And X and Z are going to be flat. They're going to be flat on this surface. To get them, so what are the exact expressions I'm not going to give, but how to get them I will show you. X is gotten by applying the angular momentum operator. So there are 3 operators here, but this is a scalar. So it applies with, let's say, Lx, Ly, Lz, or in the spherical basis, doesn't matter. And this is the scalar spherical harmonic that you've seen before. Okay, then you get X, and if you want to get Z, you just do this, I p hat cross, okay? So p hat is the direction of P at each point. So you do I p hat cross, and from X you get Z. And W, as promised, is just parallel to P. So it's p hat times the scalar spherical harmonic. What are these other numbers? What are these indexes, okay? These indexes, J and M, are the eigenvalues of operators. So let me talk about it. These operators are related to rotations, okay? And the 3 functions actually behave the same. They, if you apply J squared is just Jx squared plus Jy squared plus Jz squared. If you apply that to Q, you will get J times J plus 1 times itself. So this is an eigenstate of this operator, and the eigenvalue is this. And you might already know or guess, oh, sorry, the other one, yeah. So if you apply Jz to any of these wave functions, let's say functions on the shell, you will get M times itself. So it's also an eigenstate. What I was going to say before is that you might already guess that J equal 1 is the dipole, J equal 2 is the quadrupole, etc. And that the values of M go from minus j to j. Then you apply the parity operator. So in this case, it's r goes to minus r, but in momentum space would be p goes to minus p. And if you go through the algebra, which I will not do, you will get that they also eigenstates. Okay, they're again the same function after I apply the operator, but now they have these eigenvalues, okay, which I listed in here. And one more thing to characterize them is what I said before, okay, this polarization, in the sense that X and Z are flat on the surface. It means that they are transverse, perpendicular to P, and W here is longitudinal. So it's parallel to P. So this means perpendicular, these two, and this one is parallel, longitudinal. All right. There is an operator. The operator to characterize this behavior is IP hat cross, but we'll talk about it later. Now, let's get this XZ W to something closer to what you've seen before in other lectures. If I do an inverse Fourier transform, okay, I go from omega P to omega R by doing a 3D inverse Fourier transform from P to R, and I take the on-shell functions. See, these on-shell functions don't have a sense of what the radius is, okay? They just live on the surface, so they don't know what the radius of the surface that they're living is. But then you have to add this by this delta function, just saying, okay, you are just living on this shell. And this is just a factor for normalization. If you do the inverse Fourier transform, then you will get the m's and the n's that you've seen in the lectures before, okay? And all right, so the sentence is the on-shell multipolar functions are the 3D Fourier transforms of the regular monochromatic multipolar functions. By the way, this would be the complex ones, okay? The one that depends on the exponential and not the sine and cosine ones. You've seen both versions. And when you go to omega R space, they become these well-known multipolar fields. Maybe you've not seen this one before, or not in the lectures, I don't remember. But this one is the longitudinal one, and we'll see its role later. Just a reminder, or just something that it should be kind of obvious, they also are eigenstates with the same eigenvalues of everything. And the thing to keep in mind maybe is that for the polarization, this transverse in momentum and longitudinal momentum translates into zero divergence for M and N and zero curl for L. L is longitudinal. So it's easy to see this if you remember maybe from some wave mechanics or quantum mechanics lecture that the nabla operator, so the gradient, the nabla or del operator is equivalent in momentum space to IP. So if I am doing IP dot, right, it's like doing the divergence. An IP dot multiplied by this transverse X and Z will give me 0. So the M and N have to have 0 divergence. If I do IP cross, which is the curl, then if I apply this to something that is parallel to P, like omega, I'm going to get 0. So L has to have 0 curl. So it's easy to go from one representation to the other. All right, let's go back. So it looks like now I have a collection of complex numbers, these 3 scalar functions of omega, j, and m, that will completely characterize electromagnetic fields. Okay, if I give you all these 3, because I gave you the components on the shell, then I give you the electromagnetic field. How? There is something weird here, right? Because before I show you this kind of expansion, and you've seen it before, and there is only 2 kinds of things, not 3 kinds of things. So what's going on? What's going on, and we'll spend one more slide on this, is that the longitudinal components of the source, okay, these ones over here, that depend on L, do not radiate. You probably know this already, or do not produce fields outside. I should change this not to confuse it with, I don't mean this to be just on the far field, okay? I mean it to be, they do not produce fields outside. How do you see that? Well, one way which is quite straightforward is to remember that outside the source, the divergence of E equals the divergence of H equals 0. But this means that there cannot be any contribution from the L, right? Because the L has already 0 curl. If I already on top of it add 0 divergence, I'm going to get 0. So there's not going to be any contribution from L, which means there is no contribution for the omegas. Sorry, W's. There is another way to see it. I will mention it because it has some connection with the continuity equation. Okay, you can understand the same idea, that there is no longitudinal contributions outside the source, by thinking that the longitudinal part of the current radiates, so produces field outside, but the charge density, which I've not talked about, we'll talk about now, also produces fields outside. And then their fields cancels because they are tied by the continuity equation. You can do this, it's quite straightforward. If you remember the continuity equation, this is basically saying, this is the statement of the fact that the charge is conserved. If you go to Fourier space, you will get a relation between them, okay? Just by, in Fourier space, by the way, the derivative gives you I omega, minus I omega, and with this minus, it will cancel. But then you will see that if you think that they are radiating both of them, and you apply this, you will see that, okay, the radiations cancel. Anyhow, this is maybe less complicated and also valid to remember that there is 0 divergence outside. All right, good. Second question that you can go to the survey again. We have discussed transverse and longitudinal character of multipolar fields. Which of the following statements is the correct one? 1, longitudinal fields have 0 curl. 2, transverse fields have always 0 projection on the radial coordinate vector r. And 3, an electromagnetic field with a frequency bigger than 0 has both transverse and longitudinal components. So you can answer this now in question 2. Oh, by the way, I should mention that I believe that my slides are available for you already in the share in the cloud link, so you can have them while I have my while I give you the lecture. So I'm going to give you some time to think about this and answer. I really hope you guys do a bit better than last time. I understand these are new concepts, maybe some of them. If there's something too surprising and that doesn't add up, you can also ask a question and we'll try to discuss it. Okay, I'm going to answer this now. Let's see. Let's look at the results. Okay, now almost half of you got the right answer, which was 1. The longitudinal fields have 0 curl. Okay, we've just mentioned this a couple of slides before here. Why is 2 incorrect? Transverse fields have always 0 projection on the radial coordinate vector r. Okay. There are transverse functions like n here that actually have a component along r. M doesn't, but N does. Okay, and the difference is that, you know, we've been talking about transversal longitudinal in momentum space, not in the coordinate vector space R. And of course, 3 then is wrong, even though 17% of you answer it, because it says it has both transversal and longitudinal components, and we just explained that they only have transverse components. Of course, if you confused the notion of transversal and longitudinal between P and R, then there are 2 right questions. But when you, in the way we've discussed in the lecture so far, there is it's in momentum space, and it means that the longitudinal fields have 0 curl. 48% of you got it right. Okay, let's continue. Okay, so now we've eliminated, let's say, for now, from the picture the longitudinal components. Okay, and now we have 2 things, and the coefficients are A and B. You've seen this J bigger 0 everywhere, and I have not said why. Okay, this is important. J has to be at least 1 and cannot be 0. And the reason is that J equals 0. So if you remember the eigen, yes. So J equals 0 here means J squared equals 0. And maybe some of you know that J squared equals 0 implies scalar character, okay? So there cannot be a vector with J squared equals 0. The electromagnetic field has a vector character. We'll talk about this maybe at the end of the lectures. All right, so what we have is this set of functions, A, B for J bigger than 0, and the allowed values of M. And how do we get them? Okay, remember, this is just an expansion. If this is an expansion in basis, what I need to do to get the coefficients of the expansion is an inner product between the members of the basis, X and Z, Hermitian conjugate, and whatever function I want to expand. So that's just algebraic procedure. The correct inner function here to use, you might guess, is just the integral on the sphere. Okay, I mean, this is the only thing where these guys leave. So the correct inner product is this, and there you go. So this, okay, I told you how to get Z, I told you how to get X. This comes from the current. In principle, we are done. Okay, only that nobody uses momentum space. And doing Fourier transforms using the results from some simulation would be really complicated. So we're going to just work a little bit, and instead of getting P space expressions, we will do R space expressions. This is actually completely straightforward now. Okay. On the shell, I can expand. I can use J omega to produce the current in momentum shell. Okay, just because. So you see, instead of letting this to be a general P, now it's omega over C P hat. Okay, I'm already enforcing the constraint. Otherwise, with a P here, without the omega over C P hat, this would be not the J on the shell, but the J everywhere on P. All right, so I can do that. And one more step. You've seen this formula before. So what I'm going to do is going to plug this into here and here, okay? But I will also do something else, which is I expand the exponential with this formula involving the scalar spherical harmonics and the Bessel functions. This is a spherical Bessel function, okay? And I plug in and put it in there and work a little bit, okay? Just do some algebra. It's not very hard. You see here there is a sum in L bar and M bar, and here we have our fixed J and M, and this comes from the expansion. This is the targets that we have, J and M. And what you can find out is, out of the possible L bar contributions from this sum, given a J, which is fixed, these L bar contributions are limited to J equal L bar, okay, for the magnetic So these B's are the magnetic ones. They correspond to the X's, which correspond to the M's. And two values for the electric, okay? L-1 and L+1. Now I'm going to start using omega over c equals k, the wave number I've used to, because it's going to be easier to write. And then you have these expressions, right? So here is one term for B and two terms for A. Now these expressions, the important part is that the current, so what you may get from a simulation or from some analytical formula in R space, affects only these integrals, okay? There is an integral in R, and then you have to use then your Bessel functions and your scalar spherical harmonics. And these complicated looking integrals, as you can see, they don't depend on the current, which means that you could, if you want, pre-compute all of them. Excuse me. And the only ones that depend on the current are these, let's say, simpler integrals. So if you don't want to pre-compute them yourself, what you can do is go to this GitHub link and get a script, a mathematical script that will do it for you. For any J that you put it, it will give you the way to combine this kind of integrals to get any order AJM or BJM, right? So you can get J can be arbitrary here, and I think we've seen this. You can plug this. These are formulas at the end. They're analytical formulas, and Mathematica will solve them for you and give you the coefficients. And the integrals of R are what you have to evaluate numerically or analytically if you are lucky, and plug them in here. Okay. Let me then go back to the fields. Okay, we have this in the sources, B and A, but I need to, we were looking also for the fields mostly. And what happens is, right, as you saw this before, okay, I take this one, I do an inverse Fourier transform, I get these M's, and these are the regular ones. Okay, the regular ones contain the spherical Bessel functions in the formulas that you've seen in some other lectures. But the radiation or the field outside is produced by the outgoing ones, okay? The difference formally is just that instead of the Bessel functions, these guys inside will have the Hankel functions, okay? Of the first kind. And you force these solutions to be radiating in infinity. So they propagate energy towards infinity. Then to go from the expansion of the source on the shell here to the electromagnetic field outside, you see the A's and the B's don't directly go to the M's and the N's. You see this difference, this F? Well, these are not exactly the same coefficients, but you can work out this working out is kind of a pain because of different units and conventions of Fourier transform and so on. But you can see the details in this paper. But there is basically the point is there is a fixed way to change from the currents to the fields. Okay, and this is this factor. Okay, Z is the impedance, k squared over 2, and then minus I to the j. Okay, some factor, not very important, exact factor, but just to know that it's not directly A and B that goes into the expansion of the fields, but you have to multiply by this. Okay. All right, so we are in our expressions again. And I told you that you can just use the script and compute this and you will get the exact values. By the way, I just want to make a point that all we've done so far is exact. There is no approximation whatsoever. The only errors that you're going to make computing B and A are going to be errors due to the finite integration precision or something else due to the machine, but not due to the formulas. But it is possible to get prettier expressions that we are used to, okay? How do you do that? You do that by manually solving the p-space integrals or you can do it with the script, but then at the end you have to combine the results by hand, okay? So I do this for all the M bars and all the M's that sorry, for this fixed JM and for all the M bars, and then I manipulate this until I get something pretty. And you can do it, I'll show you some expressions for dipoles and quadrupoles, but it will get increasingly hard to do this as J grows, okay? If you try J equals 4, I believe you already will be in extremely big trouble algebraically to actually close down these formulas. What do I mean by prettier expressions? I mean something like this, okay? So I take the dipoles for J equal 1 and M going from -1, 0, and 1, which are the allowed values. And you get this expression, okay? So you go here, you plug J equal 1, you solve these integrals, you combine this according to the result of this coefficients in front, and you work a bit and you get this, okay? R hat cross J times a spherical with Bessel function 1. So the spherical Bessel function are gonna be there no matter what, because they're in the original formula. But now it looks like our previous R cross J a little bit. This one is relatively straightforward. Now, for the electric dipole, the exact electric dipole expression is something like this. And now it has this term is familiar, except for this J0. But now it has this other term here, okay? And this other term, of course, comes because, as I told you, for the electric stuff, there is 2 terms, while for magnetic stuff, there is 1 term. Okay, so you can get this kind of nicer, or like a little nicer looking expressions, or more familiar, up to quadruples in reference 11. And the group of Professor Iflukin, they derived also up to octupoles in reference 12. I'm not sure if going to J equal 4, so octuples is J equal 3, if someone is actually brave enough to try going to J equal 4. Yeah, these are, let's say, very tedious derivations. The solution for, if you really have to at some point compute higher J's, is to go to the general expressions and use the script, okay? And forget about getting pretty looking stuff like this, if you consider this pretty looking by an extent. Then there is also the issue of Cartesian versus spherical, which I will talk about at some point. So see, I'm not writing bx, by, bz, or ax, ay, az. I'm writing it with the m's, okay? And this corresponds to the spherical basis. We'll see this a bit farther in the lectures. I mentioned this now because the expressions in 10, not in 10, sorry, in 11 and 12, okay? They are exact Cartesian. So let me write down this mistake and I will fix it in the slides for later. They are called exact Cartesian, okay? In a sense, you've done, what we've done is in this paper, and what Professor Iflukin has done in his paper, is the approximated PMQs, Q is the quadrupole, electric and magnetic, now become exact, okay? So there was some long wavelength approximation in here, small source of a small electromagnetic size of the source, and now they're exact. And with this exact stuff, you can go into expressions like the far field and get it exact. The question is that is going to come up is, okay, how do we relate these A's and B's to this P exact, M exact, and Q exact, okay? And so these 2 exact expressions, descriptions must be equivalent. Okay? There's got to be some one-to-one way to go from this to this. And there is 2 issues, really, 2 separate issues. I want to try to make this clear. One is the idea that these are Cartesian tensors and these are spherical tensors. Another is that there are some k to the n factors which are not really a Cartesian versus spherical issue, okay? So for changing from the quadrupole, so J equal 2 here to the Q's, there is not only what one would really understand as a Cartesian versus spherical change of representation, but also some k to the n factors, which are not really related to this. And where do these come from? These k to n factors come from the fact that the p's and the m's and the q's in the long wavelength approximation were defined using this piece over here, this integral, and they were not using this, okay? It is only because you did this definition traditionally, it's been done with these integrals, and this has been left outside, that of course, when you don't do any approximation, this k to the n stuff is gonna pop up in this translation, okay? And it makes it quite confusing. They appear in there, okay, you can find them, how to actually apply this k to the n factors. But I want to emphasize, this is not really a Cartesian versus a spherical tensor thing. This comes from having defined the first multipolar source moments using just this integral, and because you did this approximation. Okay, so let's say there could be two ways of obtaining this in practice, okay? By this I mean the far field or the field outside the object. One is you use the A's and the B's from the currents. You translate them with this factor to the A's and the B's for the fields. This is why this F is there. Okay, and then you use the expressions that I showed you before. And two, you use the exact, so I'm talking about getting exact results, okay? You use the exact, say, Cartesian tensors and use something like this, some G1 formula before, above, which is gonna give you the exact far field, and probably you can work to make it everywhere exact as well, in quotes, because of some issue I can talk about later. But for option one, you would use this expansion of the fields, and this gives you the fields everywhere outside, except, let me just talk about the issue that I mentioned here. So it'll give you all the fields outside, exactly outside this sphere. If you use that expansion, it won't give you the fields here exactly. This has to do with the Rayleigh hypothesis. I'm not sure if you know what that is. But basically inside, you would have to use the same coefficients, the same information, the information is there, but also use the incoming multipoles. That's a more complicated issue that unfortunately it may become important in nanophotonics, because many times what we have is something that is not a sphere, and now we want to put some kind of molecule in here, okay? And you really want to know the field there. Anyway, this is a bit outside the scope of the lecture now. But I wanted to mention it in these two ways of getting the fields outside. These everywhere is going to be into quotes because of that issue. Okay.
Sorry. We have a question. Do you want? Yes. They ask is there a script to transfer spherical to Cartesian tensors, I guess, with the correct normalization?
No, there is no script. There are the translations that you can find in this paper, and I think there will also be the same kind of translations. They will be in the paper from, and they're looking here, but there is not a systematic way. But now that that question is good, there should be a systematic way because of the way this is done. Okay, you could try to write that script. The script that I announced is just producing those integrals. Okay, it's not. It's to produce these integrals, and it doesn't care about the Cartesian tensors at this point.
Okay, thank you.
Is that the only question?
Yes. For the moment, that's it.
Okay. All right. So I actually have one question. Okay.
Regarding the longitudinal components of the vector spherical harmonics, I mean the longitudinal vector spherical harmonic, is it actually possible?
You mean the L?
I mean L.
Yeah. Okay.
Yes, the one that is not here. Okay. It's actually possible to excite it in a sphere from the far field.
Inside the sphere?
Yes. but from the far field, assuming that you have plane wave illumination?
You know what? I think Christina would be the right person to answer this. I would guess that maybe not, but I'm not sure. I haven't looked in detail into this. Inside the sphere, it could be, but of course, then it will not rescatter outside. But I'm not sure.
Okay.
Yeah, we can check this. This should be in the book by Boran Hoffman, I guess.
Well, I just asked because I know for sure that in me theory, you have the direct relation between the transverse multipoles outside and inside.
And they're all transverse? Inside?
And they are all transverse, yes.
Okay,
but I always wondered if actually there was some kind of approximation with this or not.
I doubt it. I mean, because if it's in the me theory setting, then it must mean that you cannot excite L.
Okay, thank you.
Okay, where was that? Yes, okay, so we're talking about these two options. Let's call them spherical versus Cartesian. And besides these two formulas we already saw, then to compute things that you're typically used to, you use the formulas for the total scattering cross-section, for example. And in these A-B representations, they look like this for the fields. And then if you just change it to the A-Bs of the sources, it's just a different factor, but it's basically the same thing. So if you go for the Cartesian stuff, then you get it for the far field, you get a formula like that. This is built by going to Jackson and looking at all the far field contributions of this. And here is the exact expressions for the Cartesian ones. So you get electric dipole, magnetic dipole, electric quadrupole, magnetic quadrupole. And then if you go to the paper by Professor Refi-Looking, then you will find some expressions also for octopoles. Then the total scattering cross-section has also, of course, expression. It just, I would say, it doesn't look as nice as the previous ones. And also here you start seeing these factors of K popping up in there. Well, here there was before, there's no different factors of K as J changes. These are the factors of K that I was talking about. They will have to be there because of the way these Qs are defined, even though now they will be exact. But it's not completely equivalent then to the A2, let's say. Okay, so far everything was exact. Let's now do some approximations to just reconcile this with stuff that we've seen before. By the way, Adrian, how am I doing on time? I don't have a clock in front of me.
Yes, now we are at 10:24. You still have until 10:50. 10:50.
Okay, yeah, very good. We go back to these expressions, the exact expressions for the dipoles, which are valid for any source size. Okay, we can do an approximation. So this could be, let's say, a neutron star or something. And you want to compute the radiation from magnetic dipole radiation, and someone gave you the J omega r, then you just use this expression and you get the exact value. Now, if I want to assume that the source is small, okay, the thing that I have to expand here is Kr. So R is the modulus of R. So R without bolt is the modulus of R bolt. And that's basically what tells me how big my source is. So I just do the expansion in this Bessel functions. So if I do expansion to the first order, so the biggest order, which is Kr to the 0, you know that at the origin, J1, J2, J3, and so on, they are exactly 0. And the only one that survives is J0. Now, that means, okay, so I have J1 in the magnetic dipole and J0 and J2 in the electric one. So just one term survives the whole thing. And this is the term that you're very used to, okay? Integral on the volume of the source of J. Let's add one more. So we go to Kr to the first power. Now, there are two components that survive, so J2 still 0. There is no more terms added to B. So to see this, you just need to really go to the Taylor expansions of the J's, and you will see that when I go to KR to the first power, I don't add anything to here. Sorry, to here. I was doing the wrong way. I don't add anything else. This stays the same. The A stays the same, but the B adds the first term, and the first term is our familiar R cross J. All right. Let's add one more. J2 now appears, and J2 appears, and J0 picks up the new component. So now between this and this, you can reorganize things and come up with this expression here. And nothing, so when I went to KR to the second power, I did not add any term to B. So you can see this is alternating. I get one and then I get the other terms in the P and then terms in the A and so on. And you've recognized for sure this, and then you probably also recognize this. Since if we were in a live class, I would ask what this is. Now it's harder, but I'll just give you the answer that you might already know. This is what is being called the toroidal dipole, okay? Then this would be the electric dipole. This is the toroidal dipole, but in reality, you can see that it's just the second term of the exact electric dipole. Anyhow, we'll talk about this a bit later. So of course, you can continue and do this all day long. You can just keep adding terms, and then more terms will appear here. The next, so if I go J3, one more term will appear here, and then one more here, and then one more up and down and so on. I keep increasing this until I'm tired of doing this. I'm not sure why one would do this, but it's possible to do it. So let me show you what happens with the approximations. So what I have here is a current loop, right? And there's going to be mostly an electric dipole, a magnetic dipole. Here I have the diameter over the wavelength, so 2a or lambda 0. And what I have here is the relative error in the magnetic dipole moment, okay? I know how to compute it exactly, and then I will compute it using just this first term, or using this first and the other term that comes here for KR to the 3, okay? So these two lines are going to be this. This is the relative error. First term, red line, first two term, black dash line. And let's say I can tolerate, or I want to tolerate, just engineering wise, let's say, an error of 10%. So that means that if I just use the first term, I can only go to 30%. So I can go to up to 30% of the diameter. So 30% of the wavelength. The diameter can be 30% or less of the wavelength. And if I add the two terms, so I hadn't written this term over here, but I'm using 2 now, then I can go farther to 70%. Okay, this is I want to show you this to show you that if you do this approximation, this first term, which is sometimes done, you have to be very careful. Okay. I also want to mention, okay, this is probably the worst case for the error because all the current is in the outside of the radius, but you have to be careful what you do with the approximations. Well, before the break, I want to talk about the role of the spherical bessel functions. Okay, they seem to be the main difference between what we were used to and what is actually exact. Let's see what is their role. All right. So here's one question for you, not a question in the survey, but a question for you to think while I speak. We know that these terms, so these three numbers, this vector, actually determines a piece of the far field and a piece of the field outside. We've seen this before. And we also know that only the on-shell components can contribute to here. Okay, so I have the j omega r, but inside there are different components, but I know that only these ones can contribute here. So, in general, this j omega r will have j omega of p inside, and this is not j on the shell, j circle. Right? This is a general function. It doesn't need to be restricted to that shell. So if the j omega of r contains components outside the shell, but the b's have to have only components on the shell, something here is happening that is eliminating those non-contributing components. And the question is, how do they disappear? And so j omega of p is not the j on the shell, there is other components. So how do they disappear? Could it be the action of r cross? Well, that's hardly going to happen because that doesn't depend on either omega or r. What depends on omega, and the only other thing actually in this example of the magnetic dipole, is the spherical Bessel function, this k. This k, it's omega over c, it must be the one that is selecting the shell. And there is no other option for this integral to actually remove the outer shell components from here. And as you remember the general expressions, they all have a Bessel function. So this makes sense, okay? Not only it makes sense, so they all have the same structure. You can conclude already pretty much, you could conclude that the spherical Bessel functions select this correct shell out of the j omega of r. Also, by looking at this, it has to be true because this is just an angular function. Again, that doesn't depend on any radius of anything. This is angular. So it cannot kill anything on the shell. It must be this j. And you can also prove it. Okay, so the steps are, there is different ways of proving this. One of them is, okay, you take this j omega r and the whole Fourier transform, you plug it back, you expand the exponential again. Now you're gonna get some sum like that, and you see now you get this j LPR, modulus of PR, okay? Coming from the exponential is on PR, it's not restricted to the shell. And the nice thing is that this PR will combine with this KR, which is still there, right? So I've just substituted this into here and then expanded the exponential. And then I have some product of JPR on JKR. And then so you do some manipulations, and at the end you find out that this product will give you a delta function, and you will find out that this, more mathematically, is what gives you this selection of the right shell. Because I mean, you can really see it from here. Okay, it has to be this, but here you see a way to do it. Okay. And I believe this would be my last slide. Let me check. Yes, my last slide before the last question for the first lecture. So now let me make you think about something. If we do, so we have the exact expressions. We know that they are only on-shell components. And let's do an approximation. So with the first term, and we call it B1 approx. And now, okay, I have no spherical Bessel function here. Actually, the spherical Bessel function of the first kind goes to, so of order 1 goes to KR to the 3, and then you get that expression. So it's just this K now here remaining, and the R has gone into the R hat, giving you a whole bolt R. Now what happens? There is no filtering function here. There really is, you're not gonna get this delta function. So what you can conclude is in this approximated expression, this value will contain some non-radiative or non-contributing component. So it's not only that you make a mistake, it's you make a mistake with stuff that cannot be detected outside the source region. Right? So physically, let's say you are a very good experimentalist and you do an experiment, you measure the magnetic dipole, you're only gonna be measuring this. There is no way for you to measure this. Okay, this cannot be detected outside the source region. All right, so one question before the break. I hope that you guys get this one right. All right, consider the expression R hat cross J times Bessel function of the first order KR. Which of the following statements is the correct one? 1, the spatial Fourier transform of j omega r does not contain any components outside the spherical shell modulus of p equals omega over c. 2, the R-hat operator together with the integral filters out all the components of j omega r outside the spherical shell modulus of p equals omega over c. Or 3, the spherical Bessel function together with the integral filters out all the components of j omega r outside the spherical shell modulus of p equals omega over c. So that would be question 3 in the, yes, in the survey. And as before, I give you 1 minute or so.
In the meantime, we can maybe answer one of the questions.
Okay.
Well, yeah. Here they ask basically, what is the advantage of using this method if it cannot be used for calculating the near field, and compared to the fact that you can use a Dyadic-Green's function. But I think, yes, I think the student is a bit confusing the methods.
Yeah, okay, good. All right, so that's good. That's a good question, okay? I don't have the, let me go back to that sphere, that deform here, right? All right, so this method, okay, so an expansion like you compute all the A and the B's, and then where is my expansion? Sorry, I need to find this one. Okay, you compute the A's and the B's, and it gives you the AFs and the BS by that factor, and then you know these functions and you compute this. Okay, you're able to compute, let's say you compute this. This includes the near field, right? If it's a sphere, you will get the field exactly up to the sphere, up to here. Exactly, it's completely in the near field. If it's not a sphere, then you're going to, so you're going to get the field exactly up to here, right? And then in here you have to do something more fancy. But I want to say another thing, all right? If you do the expansion of the, so if you use the Green's function, yeah, you can use this and compute it here. But if the Green's function is expanded into vector spherical harmonics, multipolar function, then you get the same trouble, okay? That Green's function is not good in here, it's only good outside. If you don't do the let's say the expansion and you use the unexpanded GRR, then you will be able to compute the field here. The problem is then you're not able to look at the classification into quadrupole, multipole, dipole, and so on. Okay, that's a different. It's a different thing. You can buy if your worry is to get exactly the field here, and you don't want to do the complicated thing with the A's and the B's for here. You can use the Green's function, but then it's not going to be easy for you to tell, you know, electric dipole from magnetic dipole and this kind of stuff. I hope this answers. I think I'm going to answer the question of the survey. I cannot read it here. Okay, the correct answer. I hope this one. Oh. Results. 71% got it right. That's very good. I really thought it was going to be much more, but okay, I'll take this. So it's best to stop here now. I think this was my last slide for the first lecture. Yes. So we've done this, and we start later with toroidal multipoles. So if there is more questions, I can answer them now. If not, then we can take the break.
I have a small question. Is it actually possible to, if one has, for example, a magnetic dipole that is not centered at the origin?
Okay.
Yes, what happens in this case? Is it possible to obtain, I know for sure that if you take something and do not center in the origin, then you require more terms,
yes.
the expansion. However, is it possible to use your expansion and decenter it somehow?
Yes.
In order to,
yeah. Sorry, go ahead.
No, that's it. That's the question.
That's basically it. I mean, let's do it in the fields. It doesn't matter. I can do it in the sources. So you take, what we would do is, okay, if you have the A's and the B's, right? What you can do is let's say you set an electric dipole. So like this one over here. Now you displace this R minus displacement, and then you decompose this one into the spherical harmonics from the old origin. This is you're gonna end up using the, what is this called? The translation formulas for vector spherical harmonics to combine some of the B's, and by the way, you're gonna need also some of the A's, because so the formulas here are gonna mix quite badly for translations, okay? So here you could do it directly, right? So you come here, you do the substitution, R minus R hat and R now are gonna be different, and you do the spherical harmonics translation coefficients in here, and then you're gonna get a new expression. Yeah, it's just not gonna be just with a single J as before. You're gonna get quadruples and stuff like that. But yeah, in principle, what you say is possible to do, and maybe the easiest way to do it would be here, because the translation formulas for the scalar stuff are going to be simpler than for the vectorial stuff. Good question.
So it is not possible to directly take, for example, a Dirac delta function that is not centered at the origin and plug it into the integrals.
Well, you see, I always get very nervous with Dirac delta functions. I don't know what I don't know what to say about your question, and it is not possible or not. It could be that you do what you said. Okay, you put a Dirac delta function, but then you have to define what this dipole moment on magnetic dipole moment on the Dirac delta function is. Okay, and you would have to, if you want to try that route, you have to be quite careful with that. Formally, I think you might succeed, and then if the results that you get are the same as this with the first route that I suggested, then you're good. Otherwise, yeah, go back and check, because once you use the delta distributions, yeah, sometimes you get some surprises.
Okay.
Formally, I see no problem. Okay, I see what you mean. Okay, so it just, you define a J omega that is a magnetic dipole, and then you shift it. And there is a delta function. I mean, sure. I don't think you need the delta function, but you can use it. You can try to use it as well.
Okay, I see. Well, Professor Corbaton, thank you very much for this first part of the lecture. It was very detailed and very nice. Hopefully we will enjoy also the second part. And yes, I think this is the end of the first session. We can now start the rest.
All right.
Thank you very much.
So we have a Fourier component, a Fourier decomposition of J omega of R into P. This P is now, you know, this runs over Px, Py, Pz with some values, so pretty much can extend in principle R3. And there is no reason why this J omega of P only has components on that shell. Okay, there is really no reason for that. 2, the R cross operator together with the integrals filters out all of the components of J omega R outside the spherical shell modes of P equals omega over C. Well, this I said explicitly during the lecture, but the point is, okay, R hat cross doesn't know anything about omega, right? So it's not going to do anything or about modulus of P. So there is nothing that it can help filtering out anything outside this shell. And the correct one was 3. The spherical Bessel functions together with the integrals filters out all the components of J omega R outside the spherical shell. Okay, and this This is something that I show you. Okay, you could deduce it because the A's and the B's cannot have out of shell components, but the J omega can. So something here in these integrals has to kill those components, and it's not going to be the y star, because this is again something that depends on an angle that doesn't know anything about radiate. And this one k omega over c is doing the job. There is another way to do it. So if you just look at this kind of expression, and you look, if you remember Parseval's theorem, is going to say that the integral of on space of j times some function, and now I'm taking this whole thing, okay, as a function. This is equal, it's going to be equal to the integral in momentum space. This is Parseval's theorem, okay, of the Fourier transform of this times the Fourier transform of this. You might remember Parseval's theorem. And then you can also look into the books that the Fourier transform of this, it only lives in that shell. So there's another way where you can do that. Okay. Is there more questions? Oh yeah.
Yeah, there is a second. Yeah, there is a very interesting question. Maybe.
Yeah. So David De Vocht asks, can you also use this technique when you have multiple spheres by using superposition? You first only calculate the fields outside each sphere separately, and then afterwards interfere the two fields. Yes. The answer is it is perfectly fine. If you have the j omegas, inside each sphere, what you propose here will work perfectly. And because there are spheres now, it's going to be even easier, and you get the fields at any point in between the spheres exactly. Yes. Okay. Then maybe we proceed to the next lecture.
Sorry, a small reminder that now the question should be asked in the next section of the questions. So
okay.
lecture 2.
Yeah, let me switch myself also. All right. Okay, so we're going to talk about toroidal multipoles and Helicity multipoles. And then there's going to be some topics. I'm not sure how much of this we will be able to cover, but maybe if we are lucky, we cover all of it. I want to, if I see that there is no much time, I really want to talk about this Cartesian versus spherical, because I know this can be a confusing subject. And there will be, again, 3 more questions for you. Okay, I'm sure you've heard about dynamic toroidal multipoles. Actually, you can even read them now in Wikipedia, okay? And in Wikipedia it says, a toroidal moment is an independent term in the multipole expansion of electromagnetic fields besides magnetic and electric multipoles. Basically, you can tell the story that is being given in the literature saying that, okay, these toroidal multipoles have been forgotten in electrodynamics, but they do constitute a third independent family. Okay. And for example, the toroidal dipole. Right, so there will be, so this expression, we've seen it before actually, but you probably recognize it from the papers if you are following the literature. So basically this is basically saying that, okay, now there are 3 dipoles. There is the electric one, the magnetic one, and the toroidal one. And of course, this is also true for all the other multipolar orders. For all the other electric, let's say quadrupoles, there will be 1 more term, and so on. Okay. And what is the justification, or the evidence to put forward these explanations? It's basically always similar to what I'm going to tell you now from this paper. Okay, so so this is a metamaterial, meaning okay, it's an array of cylinders, and now one uses something exact like CST to compute some quantity, in this case the reflection and the transmission, upon this instance. Okay, so the solid black line gives you the exact answer, and then what it's done is, let's say, all right, now let me use just the standard multipoles, or by that I mean these long wavelength approximations. Okay, they use this and they find big trouble. For example, a reflection coefficient that is bigger than 1. Right? So that's, of course, not a good thing. And then they add the toroidal multipoles, and this all multipoles, this is the other line. And the match is much better. Okay, you can see it. Sometimes you don't see it because it's behind the black curve. Okay, good. But we've so let's resurface this toroidal dipole again. If you remember, what we did was before we took, so this is the exact electric dipole, and this is this expression is exact, and then we took terms in the Bessel functions up to kr squared, and then we get this and this, and this is, of course, as you, if you remember, this is the what is being called the toroidal dipole. But then, you know, we can already conclude and easily seen that the toroidal multipoles are corrections. By the way, this thing will happen also for A2s and A3s, so quadrupoles and octopoles and so on. Higher order terms in the expansion of the multipolar coefficients of electric parity with respect to the size of the source. Okay, so those, formally speaking, this is what they are. You can see that very easily by doing this expansion here. And because they do not appear in the lowest order approximation, then maybe this is why they have been, I say maybe because we don't know what people were thinking about when they were thinking about this, that they have been forgotten. All right. Okay, so that's so far so good. Now let's examine critically this statement of where they form an independent multipolar family from the electric and magnetic ones. And for that, I found that the best way was to look into the very original papers for dynamic multipoles. These are papers from Dubovich, and the history of this toroidal multipoles is first Zeldovich introduced them in the static case. Okay, and okay, there is a nice paper that you can find by Zeldovich related to parity and toroidal multipoles. But they are static, okay? And when only in the previous literature before this new wave of literature in toroidal fueled by the metamaterials and nanophotonics community, mainly Dubovich was studying them. And what this scientist did was he split, so he took some expression which was exact. It's not exact, I mean, he was not using the same kind of momentum space stuff and anything else, but there were some exact expressions. And in our notation, he split the first term from everything else, okay? Higher order terms. And the first of the higher order terms would be the toroidal dipole, but as I told you, they could be many more other terms. So he takes them all and splits these two and calls these higher order terms the toroidal multipoles, and he gives them a physical meaning. He says this has a physical meaning that is independent from the electric ones. Okay, the problem with this argument, now that we've seen the role of the spherical Bessel functions, is easy to understand. This first term doesn't have the spherical Bessel function anymore because it's been split and some terms are here, which means that it has outer shell contributions, which we know they cannot be measured outside the current. And we know that these A's will only have on-shell contributions, so it follows. So this being the sum of this one plus this one, and this one first here having outer shell contributions, it follows mathematically and trivially that this one also has outer shell contributions to cancel them. I mean, it has the same exact outer shell except for a minus sign, for sure, without actually having to even write down one formula. Therefore, this term, separately from this term, because this doesn't couple to the EM field, you can immediately conclude that this expansion, this split, cannot constitute an independent multipolar family because none of these two parts can be independently measured by means of the interaction between the source and the EM field, okay? So What you would measure, as I told you before, is this, and only this, not any of these terms, by separately. Okay. I mean, of course, in a calculation, in after COMSOL or something else, of course you can get this and you can get this, and you can, if you want, not only introduce one term, but you can get an infinite number of terms, and you can compute them all and plot them all. That's of course no problem with that. And every time that you add one, you will improve the approximation. You could also do it, by the way, this is done here for the electrics, but as you saw before, you could do it for the magnetics. There is no problem with that. But what you cannot say is that these are a new independent family, okay? In the physical sense of having an independent meaning, because you cannot measure them independently. So, well, if you want to see all the discussion, you can read this paper. Basically, formally, we know it's clear that they are high order terms, the dynamic toroidal multiples, in the electric parity multiples. Okay? And their use will improve the approximation. All right, so this explains fully the results in the literature. But they're not an independent third multipolar family because they cannot be independently measured. So from the previous lecture, we can say yes. There are indeed three dipoles. I mean, attempt to introduce one dipole. There are indeed three dipoles, A, B, and C. The only problem is that only two of them produce fields outside the source. As we saw, this longitudinal one don't produce it. I see there is a question. Maybe because this is could be a confusing topic, maybe I can answer them now. So there's a question. Is that okay, Adrian?
Please go ahead, of course.
I can read this. We know that electric dipole and toroidal one have the symmetry. Is it the same for high orders? I guess she means, Diana Shakirova means have the same symmetry. Is it the same for high orders? Yes, it's the same. Okay. So basically, the key to understand this is just this expansion, okay? So you're just adding terms in here, right? So they're adding terms on one term and another term. So in terms of what kind of symmetries this has, in terms of parities and rotational symmetries, they have to be the same because you're adding all this stuff together. And yes, if you go for multipoles that are bigger than the dipole, the same structure happens. Okay, so they are not. So you can not assign a physical meaning directly to a term in an expansion if you cannot measure that term by itself. And you could, as I think there is some proposals in the literature again, that you can do the same thing. I'm gonna have to go too far away. Instead of doing the expansion of the bessels for the electric stuff, you could do it for the magnetic stuff. And then you will get another series. And all right, so just to give you some more thing to think about, if I accept that I can measure this one separately from this one, then I'll have to accept that I can measure the next and the next and the next. And I should write that I have an infinite number of independent multipolar families, which of course makes no sense. All right, I hope that answered the question. Let us insist on this splitting, right? Because so we've seen that you shouldn't do the toroidal split because then you get out of shell components, and this forbids their measurement from the outside. But if you remember the equations, there are two terms that are again separate. I mean, they're just added together, but they are two distinct because they have both of them a Bessel function. And the question is, so this actually works for all the A's, right? So all the electric multipoles will have these two terms. So it's clear, right? Now I have a Bessel function. It will do its thing and select just the on-shell components, and then there is no out-of-shell term. So the question is, can we separately measure the two terms? This actually has been proposed, okay? In a very similar kind of split, can you measure these two terms? Now that they have spherical Bessel functions and they have outer shell components, they don't have outer shell components. Could we do that? Could we actually get this third multipolar family? Well, you know what? Maybe you can try to answer this before I give you the answer. Can you think? I'll give you 30 seconds and see if you can actually provide an answer. This is a very hard question. If you get it, I'll be quite surprised. Great, I mean, positively surprised. But I think it's worth for you to think about it for like 15, 20 seconds, okay? And if you have an answer, just write it in the question section. So it's quite tempting, right? The reason I gave you for the other split is not possible because I don't have this. Now I have them. Now, can I actually get somewhat to measure this separately from this? Okay, I don't see people answering, and I'm not surprised about that. But the answer is no. And the reason that I'll show you in a couple of slides is that each of them has longitudinal components. And the reason why you might have guessed that is that, okay, so when I did the decomposition with Z, X, W, this is a complete basis, right? It's a complete basis. I mean, so I could do some change of basis, but this one is complete. And if only two things radiate, it must be that the third one does. I mean, the third one we've seen it doesn't. So if only two things radiate, it means that no matter what I do, I'm not going to get more than two families of radiating multipoles. Let me now show you this with some pause. And we will do this change of basis. And this change of basis is going from the XZ W to these Ys. These Ys are the vector spherical harmonics, okay? So Y with no bolt is a scalar, and it has one less index. Here there is one more index here. And the change of basis is quite easy. So X and YJJ are the same. And then Z and W are linear combinations of the other two. So this L goes from J minus 1, J plus 1. Okay, so the J equals J, so the JJ I use for X, and for the other two, I just do these combinations, okay? I subtract both, or I subtract one from the other, and I get two different functions, in this case, Z and W. And as you can see, the fact that I get from these two, when I sum them, let's forget about this minus, assume the minus, I put it here, doesn't matter. When I sum them, I get something that is purely transverse, okay? So it lies flat. So Z lies flat on the surface. But then if I subtract them, I get something that is purely longitudinal, okay? That it's actually perpendicular to the surface. It must be that each of them has both transverse and longitudinal components. And actually, if you do the calculations and in one of the points, it would look something like this. Okay, now I'm taking these omega Z, WZ plane. Okay, so I'm just taking these two. So this plane that is here green. And I plot how the Y's, the Yj minus 1 and the Yj plus 1, this is for the case of J equal 1. So how do they look like? And they look like this. And now it's an obvious thing to see, okay, both of them have projections on the longitudinal, sorry, on the transverse and the longitudinal components. All right. In terms of their angular momentum properties, they behave the same. Sorry, here's the new table. This is just for your information. It's not extremely important, but so the J square and JC, they behave the same. Parity also quite similar. If I'm adding 2 of the same parity to get the Z and 2 of the same parity to get the W, okay? And the one that has opposite parity, it's the one that gives me the X. This number L square I'm not going to talk about, but this is this other index. And here's the key, the polarization, okay? The YJJ is transverse with X, but the other 2 are mixed. Okay, just with this idea now, it's easy to understand why you cannot split and measure independently those terms that we thought we could, or we hypothesized we may. Now I do the expansion, but using the new basis. And to get the taus from the ABCs or the ABCs from the taus is very easy because you just use this transformation. And then here we go, okay? So the A is a linear combination of the J minus 1, J plus 1, and also the C, it's a different linear combination of these ones. And it's very also quite straightforward to show that in those integrals that we had in the general expressions, this, say these 2 terms, this one just, it's due to this y bold jj minus 1, and this one is the y bold jj plus 1. And then the taus, the j minus 1 tau corresponds to this integral, and the j plus 1 tau correspond to this integral, obviously. And here's the finish line, all right? If I'm able, what I wanted to do is to separate these 2, okay, and call it a new multipolar family. But if I'm able to do that, meaning that I get to separately know tau j minus 1 and tau j plus 1, it means that, okay, I can take them and subtract them with using these weights, and I will get the C's, the longitudinal ones. And that makes no sense because it's impossible to get the longitudinal ones. I cannot have access to that outside the source. It means that what I tried to do from the beginning is impossible. I cannot separately measure, again, this from this. So there are 2 multipolar families that matter. They're outside the source, the electric and the magnetic ones. Okay. Let me see. There are more questions now because I'm going to change gears now. I'm going to talk about Helicity functions, and maybe I just address some of the questions. Well, now there are a lot of questions. Let's see. Aren't the Bessel functions independent? David, I don't really know what you mean. If you rewrite this a bit more, I mean, I can interpret that they're orthogonal in some way. I mean, the orthogonality relationship between the Bessel functions are, I showed you before a little bit, very quickly. I don't know if that's what you meant, but this is the only thing that I can answer now is this, okay? So if you do this integral, I mean, they have to be the same order, and then you get some delta function, so it means that they are kind of independent unless p equals k. But you might, I'm not sure you mean that, okay? So you can write again more information. More questions from Maximeric Alexander Vergès. So mixed polarizations, oh, he gave the right answer. I'm so sorry, I didn't wait. Yeah, that's the answer. That's right. Because complete basis, so transverse, yeah, that's the answer. Mixed polarizations is the answer. So you cannot have the longitudinal components in there and measure them. And Dmitry Borovkov answers, can we use expansion of the Bessel functions but take only results from that shell, right? Because others all the same cancel each other with the next term. Let's see if I understand. Let's see. See what you mean. Okay, if I go to the expansion where I have some terms at least, yeah. I mean, once you split this, okay, what you say of just taking, I really don't get it. Sorry, Dimitri.
I think he means that if the longitudinal terms cancel one-to-one with the next term in the expansion.
So the question is related to not this stuff, to this stuff.
No, I think he meant like when you expand the Bessel function.
When I expand the Bessel functions?
If you get the longitudinal components, and then each term cancels with the next.
No, wait, okay. When I expand the Bessel function like this is not related to longitudinal versus transverse. This is related to on shell versus out of shell. So if that's the question, then the answer is no. But he doesn't mention longitudinal there. Sorry, this format is not so easy to communicate. I'm sorry about that. Okay, so once you do this, all right, so each of these terms, if you do the Fourier transform of this stuff, is going to get you out of shell components. This is the reason why you cannot measure this one separately from this one. The longitudinal question comes later when you say, all right, okay, let me not do this. Let me keep the on-shell filtering by these functions, but then let me separate this term from this term. Let's try that. That also doesn't work. Guys, you can write more in the question if I didn't answer your question.
David also asked sent a clarification for his question before.
Yeah. Measure the two terms separately. Now it's clear. Okay, good. All right. So I'm going to talk about now something that is actually a change of basis that works, and you can measure them from the outside, but it's quite a different meaning from electrical magnetic. And this one, I'm pretty sure many of you have not seen before. But the idea is actually, the idea is quite easy, okay? Let me just do, so instead of using X and Z, so we're gonna keep W, but as you know, this one doesn't contribute outside, but let's have X and Z, but now I have X plus Z and minus X plus Z. Okay, so that's simple enough, and the moments now, they change in this way. And so I'm gonna call it G plus for the plus here, and the G minus for the minus. And we'll have G0 because I'm gonna identify the longitudinal one. Okay, now obviously these two are transverse, so these things are also transverse, right? Let's forget about this for a moment. It could be a bit too complicated. Basically, my point here is that when you can write all this transformation, if you remember how X is computed, which is this, and how Z is computed, which is IP hat cross X from the very beginning of the lecture, you can think of this as some kind of eigenvalue filtering. Okay, so this operator IP hat cross has eigenvalue plus 1 and eigenvalue minus 1 and eigenvalue 0, and you're just selecting from the original basis the ones with eigenvalue plus 1, and you put it here, eigenvalue minus 1, you put it here, and eigenvalue 0. That IP hat cross has eigenvalue 0 is an obvious thing because IP hat cross times this is 0. Now, IP hat cross is actually a representation of an abstract operator that is called helicity. Okay. This is a helicity operator, is used in many other kinds of physics, particularly higher energy physics. And it's really the definition. The general definition is the angular momentum projected on the linear momentum direction, okay? And that gives you helicity in the abstract sense. And when you want to say, okay, how do I implement this in this P space, then you get this, all right? All right, so in terms of rotations, how they behave, it's basically the same as before. But now the parity doesn't work. Parity is not going to be, they're not going to be, these G's are not going to be eigenstates of parity because I'm mixing one parity with the negative one, okay? So I cannot get an eigenstate of parity by doing X plus Z. I get an eigenstate of helicity, which is what I was talking about, with 1, -1, and 0 eigenvalue. And in terms of polarization, it's an obvious thing. This one has to be longitudinal, it's the same one. And these two have to be transverse because I just summing and subtracting transverse things. So these two will produce fields outside. Okay, what is this Helicity operator? So this IP hat cross is in this omega p representation, but if you want to use omega r, for example, then you can use curl divided by the wave number, again by this identification of p with IP with del. And in general, the helicity eigenstates, so in here I gave you very particular eigenstates that have some specific properties, okay? But one of the nice things about this formulation with helicity is the following. You take any two fields that are solution of electric and magnetic, they are solution of Maxwell's equations, okay? And you do this, all right? E plus minus IZH. And you apply the helicity operator, which is in this representation, let's say these are E omega r and H omega r. You apply this. And here you're going to get, guarantee you, when for the plus you get the same thing with plus, and for the minus combination, the same thing with minus. I'm going to call this, you might have heard these linear combinations, they are called Riemann-Silberstein. And Professor Bielnici-Birura is using them very much and gives lots of good theory about them. So G plus minus is, I'm just going to relabel this combination like this. This square root of 2 is just for normalization purposes. What is the interpretation? What is the physical interpretation of this? What actually are eigenstates of helicity with helicity plus and helicity minus? The easiest way to think about this, in my opinion, is interpreting this in the plane wave decomposition, okay? I have a G plus and I decompose it into plane waves, as many as the field has inside. And it happens in this case, for example, here, that there are 5 plane waves. And these 5 plane waves happen to be all left-hand polarized. As you can see, I try to draw that. Well, this, if you do the calculation, it will give you that this is actually an eigenstate of helicity with eigenvalue +1, and this G minus combination, the -1, will be identically 0 everywhere. So for all space. And this is actually quite easy to do if you just take one plane wave, okay? And of course, just take the one whose momentum is aligned with the z-axis, compute E in the complex field, compute H in the complex field, do this, and you will see that one of these two combinations vanishes. So it gives you just 0. And of course, if that works for one plane wave, it will work for all the other ones. So what is an eigenstate of helicity with eigenvalue -1? Well, when all the plane waves, as many as there were in the field, are right-handed, like these red ones here. And then it's G plus, the one that is 0. And, oh, by the way, I should mention, circular, so they are, of course, related to the handed polarization, and you have to be careful to define it with the right or the left hand correctly, so this sign is not confused, because there is this different conventions of define circular polarization from the point of view of the of the receiver or the emitter, and this is quite confusing. But if you use your hand to put your right thumb along the right or left thumb along the axis and see that the other fingers are following the curvature of this picture, then you will get the right answer, whether it is left hand or right hand. In general, of course, you take a field that you don't know about and you do the decomposition, let's say, and of course there will be mix, and there will be G plus different than 0 and G minus different than 0. All right. So as you can see, this G plus minus is a generalized polarization handedness. Okay, it's just polarization handedness for any field that can be decomposed into plane waves, and it does work for all the fields, far field, and also the near and evanescent fields, because you can also define a handedness in an evanescent field. It's only hard to draw here, but it also works. So you can have a near field of pure handedness, for example. I'm going to talk about now symmetries a little bit to connect this Helicity operator to a particular symmetry. So you've seen this before, okay? So rotational symmetry conserves angular momentum. What does it mean? It means that, let's say I have a target like this. So this is some disk with some material and there is some hole in it. And as you can see, this disk is rotationally symmetric if I rotate it like that. So if I come in with electromagnetic beam with some defined angular momentum, with an optical axis that coincides, with this axis of the cylinder, what I know is that, okay, the scattered field could be much more complicated and different from the incoming field. So you may come in with a Gaussian, and then later you have this more complicated scattered field. But one thing that you know for sure is that the angular momentum of the scattered field will be the same. Okay, we'll have the same eigenvalue. And it's the same story for linear momentum. Okay, now it's related to the translational symmetries. And just to illustrate that the symmetry language goes beyond electrodynamics. What happens if I have an infinite wall like that, and I have this ball, this billiard balls, and I use the Q1, I touch the blue one, and now it's going to bounce back. And if I ask you at which angle is it going to bounce back, you all going to tell me at the same angle that it came in, very intuitively. And the actual fundamental reason for this is that this translational symmetry in this direction is conserving, doesn't change the momentum in this direction. So let's say in this macroscopic picture, the velocity in this direction. So it has to be moving at the same velocity, and for that, it needs to be bouncing at the same angle as it came in. And then, of course, Fresnel formulas also give you that. And again, you can tie it to linear momentum conservation. Okay, so Helicity is also tied to a symmetry, and this symmetry is called electromagnetic duality. And I'll tell you the expression later, but I want to show you the behavior now. So this is a dual symmetric object. I come in with some pure handedness. And by the way, I could have put here lots of other plane waves as long as they are blue, left-handed. And the dual system will not change the handedness. It's the same thing, okay? Here it won't change the angular momentum. Here it won't change the momentum, the linear momentum along this direction. And here it won't change the handedness. So the regular behavior would, of course, be that there is some components of changed polarization handedness. But a dual symmetric system behaves by doing this. And if I come in with red here, it will all be red outside. Okay? So this is the expression. So just look at the first expression here. So the first line. This is the expression of the duality symmetry. Okay, this combination of the electric and magnetic fields. And you might have seen this before. Okay, maybe you've seen it in the discrete version when I put theta to pi over 2. Yes, to pi over 2. And then I get that E is equals to minus H, and H equals to E. This you might have seen before. It's just the discrete version of the continuous rotation that is like that. See, this is a rotation on the EH space, not a rotation in space, all right? It's a combination of electric and magnetic fields that looks like a U1 rotation. If I change the basis, if I do this, so you can really think about electrodynamics with G plus and G minus instead of E and H, because the only thing I did here is really a unitary change of basis, right? So it cannot be that I broke anything by talking about G plus and G minus because this is unitary and I can completely invert it at any time I want. So it has to be equivalent. The physics have to be equivalent under this unitary transformation. It may or may make things more easier or complicated to change the basis, but it cannot change any fundamental property. So if I do that change of basis, that transformation looks easier, obviously, because these are eigenstates. And the G plus, the rotated G plus is just the original one times this phase, and the rotated G minus, or the dual transform G minus, is this original one times this phase with the different sign here. Okay, now I told you what a dual object does, and how do you get a dual object? Well, it's very hard to get a real dual object in optics, but let's see why. If you're talking about macroscopic equations, if you're modeling your scatterers with, you have your dB as a function of some matrix, let's call it, this is 6 by 6, and there are 3 by 3 block matrices here. And then you have your EH. Then you can show that the G plus and the G minus live separate lives. So they decouple, they don't mix. If and only if epsilon is equal to mu, and you heard about this before, and chi equals to minus gamma. Okay, if you have a material that does this, then you can decompose really electrodynamics inside that material into two separate things that don't ever talk to each other. This is very different, okay, from the E and the H fields that they always talk to each other with Maxwell's equations. Okay, there is another approximation into which you can also express the condition of duality, and actually this one allows you to get some more realistic objects that behave almost dual. In the dipolar approximation, what you are doing is, okay, I have again a 6 by 6 matrix, but this is a polarizability tensor now. And this tensor allows me to take the E and H fields in the position of that object, which has to be very small because I'm going to just use the dipolar approximation and forget all the quadrupoles, octopoles, and so on. But this, through this matrix, induces some electric and magnetic dipoles, and these are the ones that radiate. Okay, and the field that they produce outside will be of the same handedness. Imagine that I can combine, so this is circularly polarized. It will be of the same handedness outside the scattered field if basically the same condition. The diagonal terms are equal and the off diagonal are equal except for a minus sign. Now there is some change of units here because epsilon, this is the epsilon and mu of the surrounding medium, but essentially it's basically the same condition. Okay. Let's look at,
we have two questions.
Okay. Yes. Yeah.
Okay. So the first is from Maxime. How do you take into account the eigenvalue 0? Does it correspond to linearly polarized light?
Oh, good. No. All right. Good. Good question. The eigenvalue 0 of Helicity is the one that is the longitudinal wave function. So all the longitudinal functions, and this one we don't take into account. Let's say outside the source because it doesn't matter outside the source. The linearly polarized light is a G plus and a G minus, a combination. You have to, for example, the simplest example is I take this plane wave and I sum them to this plane wave, okay? And now I get a linear polarization, a G plus and a G minus. If I change the sign, instead of sum, I subtract them, I get the opposite, the orthogonal linear polarization, right?
Also, Dimitri clarifies the previous question. Okay. Maybe you can just read it because it's very long.
Oh yeah, it says please after the end of the lecture. Okay, maybe I can look at this at the end of the lecture, sure.
Okay.
All right, we were talking about dual stuff. Let's go first for this, okay? If you try, so there is no natural material and optics, and maybe in many other frequency bands that actually does this. At gigahertz and below, I think at megahertz, there is some ceramics that can do epsilon equal mu. but this actually is not, so this condition is needs to be true if your material is not isotropic. If the material is isotropic, this actually relaxes a little bit, just a little bit. So if it's isotropic and I have some four media here, they are together. Now this is not, these epsilons and mu's are not matrices, 3 by 3 matrices anymore, but they're just scalars. And if I have this, and I meet this condition, right, mu over epsilon is constant everywhere, then the helicity will be preserved in this system. Okay, so it means that I can come in with some G+, let's take it from here, and this is going to do lots of weird things. Okay, you know, it's going to bounce around and whatever. I don't know what it's going to do, but one thing is that if you are able to get this, then you will know that there will not be any G- component anywhere in the system. Okay, so, and this is independent of the geometry. Of course, again, you're gonna have to get mu's different than 1 and relative mu's different than 1, and that is hard to get, particularly in optics. Now, how about the other one? When we were talking about the dipolar duality, all right? This you can do with non-magnetic stuff. For example, a non-magnetic sphere with mu equal 1. So this is the relative mu again. So you have to meet these conditions, the dipolar duality conditions, and I'm putting a 0 here already because I'm going to consider a magnetic sphere that is not, sorry, a dielectric sphere, and it's not chiral, and these cross terms vanish if I have parity symmetry. So if it's a sphere that is not made out of chiral stuff, this will be 0. So this is already for free, okay? So I have two conditions, but in a sphere that is not made of chiral material, then this is 0 already. So I have to meet this one, electric polarizability equal to the magnetic polarizability. And you might already know that this is actually possible. Right, so we have a sphere. This would be the regular behavior. There will be some change of helicity, meaning that this is not dual. And here is the power, so what I'm plotting here in the false color scale is the power of the helicity change. So the power of the red component divided by the total power of the scattered field. And this is the radius of the sphere in units of wavelengths, and this is the electric permittivity. By the way, for this calculation that you can do with me theory easily, the surrounding refractive index is 1.3, but that doesn't make a difference, it doesn't make a qualitative difference, correct? It makes some quantitative difference that, well, this region here, where the helicity change is very small, will maybe move around, but there will be one, okay? So you can see that for some radius, smaller than small, and of course you want that anyways because you're assuming that the quadrupoles are 0, which are not, but let's say they're small enough. There are some permittivities, which are typically high, all right? But you can get this area here, where the change of helicity and hence the duality breaking is quite small. This 10 to the -3 here means that, for each photon that is red here has changed helicity, I have 999 that are blue. So it's not perfect, but one can do maybe something with it. And this something can come, you can also do this with cylinders, although then for cylinders, you really need to fix the input to the axis of the cylinder. For spheres, of course, if you have a sphere here, it works no matter what, no matter which direction of incidence. But for cylinders, it's going to only work for one direction. You can do it for cylinders as well. And for coarse shell spheres also are good because they let you make this smaller. Okay, so you can kind of do this practically at this point. And what are the applications of such systems of dual response? You might heard of zero backscattering. Okay, so you build a system where if I look at the energy that comes exactly back towards me, so after the illumination, this is 0. And you will know about the Kerker condition, and you will recognize that the Kerker condition is this A1 equals B1, electric equals magnetic. So in this case, Kerker, when he did it, he had epsilon equal mu spheres. So that, of course, is much better because then you're not only dipolarly dual, but you're completely dual. Right? So zero backscattering is one application. The sensing of chiral molecules is another one because of what I told you before. You can have near fields of pure handedness, and then you can put the molecules in there and do interesting stuff with that. But of course, for the near fields to be, so let's looking at the near field of this. If you want this to be all blue, then you better have the sphere here, okay? And okay, this is only now for illustration because in reality, if you have a sphere, even though it's small, in the near field, the quadrupoles are going to matter and the octopoles as well, probably. So this is only for illustrations. You can do it with disks a bit better. They have been also suggested for topologically protected surface modes. Okay, I think that these dual materials were studied by Professor Mario Silveriña, and you can just type his name and topology protection, and you will find that paper. But basically, just wanted to say that there is some application to try to get this kind of response. Okay. Before I change gears, just obviously the way we produce the Helicity multipoles, like this, right? B plus A and minus B plus A means that I can just use the same expression, the exact expression that I had for B and A, and produce the exact expression for G plus and G minus. Okay, that's obvious. And for the dipoles, for example, I did it here. For the pretty looking ones, not for the ones that you need to compute the momentum space integrals. And then you get some, okay, so you get some function. And the interesting thing I would say, maybe the difference is that now I get the Z0, J1, and J2 at the same, together. And lambda here is the helicity plus or minus, and it just changes the sign here. So you can also get the handed radiation out of these formulas. If you want, you can expand them, so you can approximate them. I don't know when you want to do that, if you actually are able to use the exact expression, but you can. And okay, so what I'm talking about, a dipolar emission of pure helicity, right? So there's a cartoon, probably not very accurate, but the point is you have a dipolar-like radiation pattern, and if you decompose the plane waves, all of them in helicity plus are left-handed and helicity minus are right-handed. And again, I don't really draw here the evanescent components, but those ones will also be all blue and here all red. All right. Oh, question for you. Okay. So that's question 4 on the, let's see, on the survey. Let me go to it. Yes. Select the correct option to finish the sentence. The helicity operator, 1, is connected to spatial rotations. 2, has 2 eigenvalues. And 3, the helicity operator applied to a longitudinal field gives the 0 field. I'll give you some time to answer this.
I remind the participants that you can answer Corbaton's question in the tests and surveys section. I think that on the meantime, we can answer the questions in the chat.
Yes, we can.
So do you want to read them or?
Let me see. Questions. Practice on the, hold on. Let me read them. Okay, there's one very long one that I said I will look at later from Dimitri. Okay, another question from David Deboch. For the dipolar approximation, do we then consider the medium is homogeneous regarding to epsilon? Yes, yes, because for the macroscopic matrices, we consider a tensor for epsilon. Yes, no, sorry, just in case that is not clear. Yes. So there is a surrounding refractive index, and the sphere is made out of a simple electric permittivity. Everything is isotropic, and it's not homogeneous in the sense that there is a sphere, but the materials are. And David Alexis Garcia Espinosa writes, To design a not dual material, yeah, that is very easy. Is it enough to guarantee that you don't get that ratio, so the mu over epsilon is different? Yes, that's enough. But actually, to design a non-dual material, you can basically pick up any material. You actually have to work hard to get these components to be very small for general objects. Okay. As I said, I think there are some kilohertz, megahertz, and so on materials, artificial ones, that they actually manage to do epsilon equal mu. And then, of course, you can choose any shape. You see now, contrary to this shape independence, which you can achieve if you get, say, epsilon equal mu, now I depend on the specific radius of this. Okay, so if I move a little bit from the radius, I'm entering an area of very high helicity change. So I have to be precise here. That might be also a problem for fabrication. I'm not sure. But for doing a not dual system, yeah, that's we can do that anytime. Oh yeah, the question, is there more questions? No. So let me, I'll answer myself the survey. The answer, I finished. Let me see the results. Well, a third of you got it right. The Helicity operator, let's go one by one. Is connected to spatial rotations? No. As I think I said explicitly, angular momentum is connected to spatial rotations. And helicity and the duality symmetry is connected to these rotations in E and H space, which are not spatial rotations, okay? These are not rotations of R. So one is wrong. Has two eigenvalues. It was a bit tricky, I have to admit. It really has three eigenvalues. One of you asked the question, what happened with eigenvalue 0? Yes, +1, -1, and 0. It's only the helicity operator really only for radiating stuff, or then only has two eigenvalues, but not in general. But this one was clearly, obviously true. The helicity operator applied to a longitudinal field gives a 0 field, but precisely because the longitudinal field is the 0 eigenvalue. It's an eigenstate with 0 eigenvalue. Okay? All right. If there is no more questions, I will go on. I cannot see questions. So there is no more questions. Another change of gears. So the last, since the second lecture, as you can see, it's kind of a specific, more, I wouldn't call them advanced, but maybe more uncommon topics. We've been talking about, you know, the J, RT, which you can think of is ultimately due to charge. So ultimately is due to movement of electric charges. But there is something else that produces electromagnetic fields. And you may or may not know this, but I'm going to call it M. And this is ultimately due to the intrinsic spin. Right? So we know that electrons and protons and neutrons have some spin. And that depending what you do with it, how this spin, let's say, moves. So spin, contrary to charge, is already a vector, okay? Charge is a scalar, a spin is a vector. Depending what the spin vector does on these things, you get a signal outside. And you probably have even experienced, some of you, an NMR, nuclear magnetic resonance. These guys radiate, and these are due to spin. And this is a medical diagnostic tool that is very important. And also, it's also extremely important for spectroscopy. Okay, so in a sense, we have been doing half the job, right? We had, so both kinds of sources. Yeah, then a different question is whether this is important in optics or in other bands. That's, of course, separate. Like, for example, the spin doesn't particularly enter any optical process, at least the regular ones that we use. And but that's besides the point, okay? In general, we are doing half the job if we only compute the A's and the B's using the J on the shell, right? So really, this A is not only a function of J on the shell, it's also a function of M on the shell. By the way, the proofs that you have to be on the shell is basically the same as for J. So we really should be considering these two inputs to each of these A and B expressions. Well, how can we go about this? Well, we still know that the Maxwell's equations are linear, right? So I have one kind of option, one kind of source, and I add the other. What I could do is, okay, I compute A for J equals 0 and some M, and B for J equals 0 and some M, and I add them. So I add A and B to the previous ones that I had computed with the opposite, with the 0 on the other side, right? So I had J0, J0, and I could take those plus those, and I'll get the right answer, and that's true. And it's actually even better in the sense that, well, maybe now we need to derive new expressions for when I have my my source here instead of here. And in reality, you don't have to. You can see this is an easy way. This is an easy proof. Okay, you can see in this paper that if I want to compute A of 0M, I can just compute B of a J, a virtual J or a change J, that is Km and 0 here. So these expressions we have, okay? B of something 0 we have. Those are the ones we've been using the whole lectures. A of something 0 we also have. But it happens that A0M is equal to B K Km 0, right? So we don't have to derive new expressions. We can use the old ones, and we have to be careful to flip electric and magnetic stuff. It's not, I mean, it's really not a coincidence that you're flipping electric and magnetic stuff because you go from charge to spin, but that's a bit besides the point. So we can just reduce the expressions that we use for J, and okay, J in the shell, and then the other ones with J omega R and the Bessel functions, and then we just use them for M omega R and the Bessel functions. And it will work, which is good news. And okay, I'm not gonna say much more about this here, but remember I told you about maybe some nice applications to talk to molecules with things like this, okay? Let's say, what are the conditions now that we have all the story with the sources complete? What are the conditions so I actually get such kinds of handed radiation? Something that actually has only one handedness, either plus or minus. What are the conditions on the sources to get purely handed, so pure helicity electromagnetic fields? Well, it's quite, algebraically it's very easy. Okay, I just have to have either the G plus is 0 and I only have G minus, or the G minus is 0 and I only have G plus, right? So either A equals minus B or A equals B. Fair, easy enough. Now, how to get that? What conditions that this impose in my sources? It's a bit more involved, but not much. Remember what we found out before? Okay, so the A's for JMs are the A's for J0. This 0 should be a bold 0 because these are vectors. Let me write this down. And so it's AJ0, B, KM0. And the B's are like that, okay? Now, how do I get all the A's equal minus B? So this equals minus this, or this equals this. There are three main ways to achieve this, okay? One of them is if J equals either plus or minus Km. And this is kind of obvious, right? So if J equals Km, and I plug it here, right? I will be summing in this line A Km plus B Km and 0, 0. And in this line, I will add B Km plus A Km. So basically, this total A and this total B is going to be the same. So I'm going to get this condition. Good. And with a minus, I'm going to just put a minus in the right place, and I'm going to get this condition. Right? So if I just, instead of changing this j for plus km, I change it by minus km in there. You will see I have minus a plus b, and here I have b minus a. So the total combination on this line is minus the other. The problem or the thing is that if you want this solution, for get 100 sources, you need both kinds of sources. Besides that you need them to be in this relationship, you also need them both. You need the electric and the magnetic sources. Then you can do something else, okay? Let's assume that the magnetic sources don't matter, maybe because we're in optics. Then you can very easily prove that if the J on the shell is an eigenstate of helicity, okay, with eigenvalues plus minus 1, it's on the shell and it's on the transverse. Of course, this is only the transverse part if you want. If it's like that, plus minus 1, I also am able to get these conditions. And it's actually quite easy. If I take just the transverse part of the J on the shell, and I apply IP hat cross, you know that IP hat cross X gives me Z. So I'm going to flip this X is going to be a Z. And I haven't told you, I skipped over it, but IP hat cross squared is the identity for the transverse functions. Then, okay, maybe I'll show it. Sure, if you. So IP hat squared on the our transverse function, you can write it. It is going to be minus p hat cross. Okay, I'm just expanding the square here. And then by the properties of the cross product, you can decompose, you can expand this into this. Up to here, there is no special requirement on X. Okay, this is true for any X that I put here. But you see the first piece, P dot X. For our transverse functions, X and Z, P dot X is 0. So IP hat cross squared is just X times P dot P, but P dot P is 1. Hence, this is the identity when it operates on X. And it's going to be
20 minutes.
20 minutes, yeah, it's more than enough.
Mm-hmm.
Thank you. So then, when it operates on transverse functions, this helicity square is identity. So in reality, this line there, so the X went to Z because one time that I apply IP hat cross, but the Z itself is already IP hat cross times X. So IP hat cross here, square, is going to give me X. As you can see, I've changed the electric stuff for the magnetic stuff. Not unexpected, because the helicity operator, it's related to the duality symmetry that does exactly this. And of course now, it's if I want this, all right, I did IP hat cross J, and I want it to be equal to either plus or minus itself, I'm going to have to either have A equal B, right? The Z's have to be now corresponding. So the coefficients have to be equal. So either A equal B and B equal A, which is the same one, or A equals minus B for the other sign. And then again, I will get this pure 100 source. This is actually what happens for that sphere to the dipolar approximation, okay? For mu equal an object with helicity present response, this on the shell, this current has to be an eigenstate of helicity. Of course, you can do the same by asking for M to be an eigenstate of helicity on the shell and J equals 0. Okay, the next question, one before the last question. Which of the following statements is the wrong one? 1. Neutrons cannot produce electromagnetic fields with omega bigger than 0 because they are neutral. They don't have charge, meaning. 2. The expressions for AB due to the electric current density can be obtained from the expression for AB due to the intrinsic spin. And 3. When both charge and spin produce radiation, it is possible that such radiation has only one handedness in it. I'm asking for the wrong one. Okay, there are 2 true statements and 1 wrong statement. I'll give you a couple of minutes. Okay, maybe, I hope that this time was enough. Let me go answer this. Which one is the wrong one? Okay. How did you do? All right, now more than half of you got it right. The wrong one is 1. I mean, yes, they are neutral and they cannot produce electromagnetic fields through J, but they have spin, so they can produce electromagnetic fields through M. Okay, so this one is correct. Sorry, this one is wrong, and this is the answer. The answer is 1. 2, I mean, this we already said, right, that the expressions for the AB due to the what we said in the lecture is that AB due to this intrinsic spin can be obtained from AB due to the electric current density. Of course, the opposite has to be true. So if I have expressions for the AB due to the electric current density, I have to be able to get the others. So it's quite trivial thing. And then when both charge and spin produce radiation, it is possible that such radiation has only 100 in it. Sure, this is the first way that we just discussed. There is charge and spin, they produce radiation, they are on the shell, and they have transverse components. And if they're related like this, they will have only 100 in the field. Okay? All right, I want to talk about these irreducible tensors, but let me see if I can do one thing. It's going to be too hard. No, it's going to be too hard to split it. I was going to talk about Cartesian versus spherical before, but I guess I have to do it in the predetermined order. So you might have heard this, irreducible subspaces, irreducible tensors, and the sentence that I want to explain is this. The AB contain irreducible subspaces under rotations and parity. All right, so what does it mean? We have to go slow for this. I'm going to do a rotation of the source. We have our source, and now I rotate it, okay? And now the question is, given the original, AJ omega, BJ omega, what can we say about the new AJ omega, BJ omega, and this R here is because of the rotation. So what can we say about this? Well, the thing is the following. Let me fix J. If I fix J, I mean, I'm not going to prove any of this, okay? I'm just going to try to explain what these irreducible subspaces and the rotations and parity mean. What you can show is that the rotated coefficient, the coefficients for the rotated source, given a fixed J and for all the values of M, are a linear combination of the A's. Okay, so the A's, the rotated A's are the linear combination of the rotated J's. Sorry, the rotated A's, the previous A's, and I don't need any other J. Okay, so from this three, so for the dipole, from these 3 numbers, I can get the 3 numbers. And for the other parity, for the magnetic one, for these 3 numbers, I can get the 3 numbers. So they are just linear combinations. Meaning, the different values of J do not mix under rotations. Another way of saying this, dipoles stay dipoles, quadrupoles stay quadrupoles, etc. And these linear combinations are actually, these coefficients are given by Wigner matrices. I'm not sure whether you know about them. I'm sure I know some of you do. And the Wigner matrices are some matrices that depend on the multipolar order, so the J value, and 3 angles, alpha, beta, gamma, that correspond to this way of writing a rotation. So a general rotation R, you can always write like this. First rotation along the z-axis by gamma, then y-axis by beta, another z-axis by alpha. Okay, and then there are programs in MATLAB and tables to get you these matrices. Okay. Another kind of language that you have heard before, the sets of objects that transform like this, okay, with these matrices, are set to transform as the jth irreducible representation of the rotation group. And what it means, irreducible, it means that they don't couple upon rotations. That's what it means, right? That's one of the things that it means, but one that I find particularly easy to understand. So, okay, we did rotations, and now we can do parity. The point with parity, as I showed you before, is that the x and the z's are eigenstates of parity, so they don't mix. And hence parity is not going to mix their coefficients, the a's and the b's. They don't mix them. Plus, also parity doesn't change under rotations, and they don't change j and m. So, I mean, another way of seeing this is that parity commutes with any angular momentum. Not very important. The point is that now the whole statement here is that if you fix j, the a's are irreducible under ON. So this is the rotation group plus parity. And it means that they don't mix with other j's, and also the a's and the b's don't mix. That's basically what it means. All right, so this is the last question. Select the correct option to finish the sentence. The parity transformation, 1, changes dipoles into quadrupoles. 2, changes electric multipoles into magnetic multipoles. And 3, leaves the longitudinal multipoles invariant except for an overall phase factor. Again, I'll give you some time. So now I'm asking for the correct option.
There is a question in the chat if you want me to read it.
Yeah, go ahead, please.
From Deepak Kumar, in which aspects toroidal dipole mode is similar and different from other multipoles? How challenging is it to excite it and detect this mode?
Okay, let me go myself to the question. I think I understand it. There's one that you cut off for a while there. Questions. Similar, different from other multipoles, how much challenging is to excite and detect toroidal resonance modes? The answer is very challenging, actually impossible. Meaning, if you're talking about something that is different from electric, in the sense of different from the exact electric dipole, then that doesn't exist. The toroidal dipole, the way that is defined in the literature, you cannot excite this from the outside in the same way that you cannot observe its radiation from the outside, independently, okay? Independently. As a sum, I mean, in a COMSOL simulation or anything like that, that's different, but you're actually asking something that sounds like a physical question. How much challenging is to excite and detect toroidal resonant modes? There is no real toroidal resonant modes. Those are electric resonance. Okay, they are. So let me go back to this some time ago. Okay, yeah. So if you plot the spectrum of this, it will have up and downs, okay, right? And maybe one of the up and downs, it's produced by this thing over here, more than this thing, okay? Maybe not exactly all of it, but maybe it's produced by this more than this. And then the question is, are you calling that a toroidal dipole resonance? So that's, okay, you're giving some name there, but it physically doesn't mean anything. It's still electric. I hope I answered the question. Okay. Q5. And I'm gonna Now go to the survey. Oh, I already cannot do the survey. Huh. Hold on.
It's question 6, Professor Corbaton, I think.
Oh, sorry guys. Let me answer. Let's see. All right, 80% of correct answer. The maximum in the, okay, I'm very glad that the last one is the one that you guys get the correct, the most of you. So I just said in the previous slide, right, the parity transformation doesn't change stuff for rotation, so it's not going to change dipoles into quadrupoles. And the electric multipoles and magnetic multipoles are actually eigenstates of parity. They're not ever going to be changed by a parity transformation, and we've seen this throughout the lectures. But this is true. Okay, it leaves the longitudinal multipoles invariant. It's because longitudinal multipoles are also parity eigenstates, except for an overall phase factor, which is the eigenvalue. Good. All right. Okay, let me just go. I want to have enough time to discuss this Cartesian versus spherical basis, because I know this is a confusing thing. Let me just go quickly through this. Okay, I take the two vectors of dipoles, so electric and magnetic one. Okay, this transforms as a vector under rotations and has a definite parity. And this is the key question, okay? Transforms as a vector under rotations, or as we said before, transforms as the j=1 representation of the rotation group, SON. And what it means is, if I, instead of writing B1, B1, B0, B minus 1, or in this case, A1, A0, A minus 1, which is the spherical basis, I were to use AX, AY, AZ. This is just a change of basis. This j=1 representation of rotation group means that, for example, the rotation by Z with some angle is just looking like this, right? Okay, and this, why did I change to Cartesian? Because you most likely can recognize this form. And now let's talk about this Cartesian versus spherical, okay? For dipoles, first, only for dipoles. So we can write a vector A, for example, in the spherical versus vector basis like this, okay? A1 times E hat 1, A0 times E hat 0, and A minus 1, E hat minus 1, and we are defining E hat 1, E hat 0, and E hat minus 1 like this. I'm just doing a change of basis, and of course the vector itself, that's something that doesn't depend on the coordinate system. It's actually a physical thing, in this case, an electric dipole. Then it has to be equal when I go to the Cartesian basis, X, AY, AZ. Okay, and given these transformations for the basis vectors, the coordinates transform accordingly. This is something that you can work out in 10 minutes, or you can look it up in a book, which is better. So the A1, A0, A minus 1 for the spherical basis, it's obtained from the XYZ with this matrix, and the other way around, from spherical to Cartesian with this matrix. And this is a unitary matrix, okay? A change of basis that cannot change anything. This doesn't change any physics, any number of degrees of freedom. I have 3 degrees of freedom here and 3 degrees of freedom there. So there is no difference at all in the physics. I cannot have any kind of problem here. So for dipoles, Cartesian versus spherical is just a change of basis, all right? Let's go to quadrupoles, which are more interesting. So dipoles,
2 minutes.
2 minutes. I think I'll just finish this then, and I won't go into the other stuff, but I'll finish the Cartesian thing. They transform, so a quadrupole, so I have here my quadrupoles, right? So say j=2, and then m=2, 1, 0, minus 1, minus 2. They will transform at the j=2 representation of the rotation group. Means that when I rotate it with this matrix, I get some other matrix here that I don't know, I didn't write it down. It's more complicated. It's certainly not this, okay? Even if I put the Z rotation on the Z, sorry. Certainly not this, okay? First of all, it's already 5 by 5, okay, as you can see. And okay, and then transforms in this way. Good. I have 5 components. The problem is the Cartesian quadrupole, as a quadrupole, It's just adding xx, xy, xz, yx, yy, yz, zx, zy, zz. Now it has 9 components. And now we have a problem, right? Now 5 versus 9. What's going on? It's been mentioned before. What you need to do to reduce this 9 is the following. You have to impose that this matrix is symmetric. So yx equals xy, ayz equals azy. So this equals this, this equals this, this equals this. Plus, you have to get the trace of this to be 0. And then, and only then, okay, you have left with 5. Okay, I had 9, and I have 1, 2, 3, 4 equations. So 9 minus 4 is 5. And now there would be a one-to-one unitary change of basis between these 5 components and this Cartesian 5 components when I impose this, okay? Why do I have to remove this? It's actually interesting, because the trace of a matrix doesn't behave like a quadrupole, it behaves like a scalar under rotations. It doesn't change. And you might have heard that the trace is invariant under rotations. And this antisymmetric part, so which I kill by doing this, behaves like a vector, not as a j equal 2, but a j equal 1. So I have to kill all of them. Now I can compare the two, and it has physical meaning as a quadrupole. So, of course, when you go for bigger j, so as the multipolar components for this should be j bigger than 1, okay? When j is bigger than 1, so not the dipole, there is not a one-to-one correspondence between the Cartesian things that you can just obtain by piling up x's and z's and y's, and the actual degrees of freedom, which are 2 plus j plus 1 spherical components. So for the Cartesian components, you have 3 to the j numbers, and here you have 2 j plus 1 numbers. So once you go with j higher, you have to start thinking about this kind of stuff, remove all traces, remove all the antisymmetric tensors, and then you get a one-to-one. But otherwise, it's a dangerous business, and it can be very confusing. I'll finish this. I'll just say that in this discussion, I have not invoked these factors of k, okay? As I want to say it again, these factors of k that appear in the conversion between the spherical and quote Cartesian don't come from the mathematical of the tensors. They come from the expansion that was done to define the p's and the m's and the q's. So I stop here, and I thank you very much for listening for me for so long. And that's it. If there is questions, I can address them now. Oh, there is at least one, right?
Yes, thank you very much for your talk. It was fantastic, very clear.
Thanks, Adrian. Yeah. All right. Okay, there's a few of them.
Yeah. Deepak Kumar, if I'm pronouncing your name correctly, you can just look at the recording afterwards.
Yeah, I answered, Deepak, I answered you actually. Maybe you can, in the interest of time. Ramil Minuyan, can you please explain again the physical meaning of the fact that only, okay, all right, from the very beginning. The physical meaning, well, okay, so those are in a sense, mathematical proofs, but the physical meaning is similar to saying here, okay? When I have stuff that is on the shell, when I put this delta here, okay, and then I get the right multipole, okay, that produces the outgoing one. If I don't have this, I'm not going to get a solution of Maxwell's equations here. That's another way of seeing it. It's one way that it doesn't involve so many maths. But the idea is, you can also think about it, okay? How do I? So imagine that you have a component that doesn't meet that. Okay, let me go to the beginning. So you have a plane wave component of the j omega of p that doesn't meet this, okay? That has px squared plus py squared plus pz squared different than omega over c squared, all right? And now the question that you can ask yourself is whether now, so I have this component there, whether now Maxwell's equations are going to change the fact that this is not equal. Because I know for a solution of Maxwell's equations that radiates an electromagnetic field, I need this equation, this equality, right? It has to be equal for the E and the H. In the Fourier domain, I have to get this. Otherwise, this is not a solution. Now, the question is whether Maxwell's equations is actually taking everything outside the shell that doesn't meet this and makes it meet this. And you can quickly realize that this is not going to happen. I don't know. I don't know how to, on top of my head, more other proofs. I mean, I recommend you to read this paper. And it's actually an interesting one, just from other points of view. But in there, they will also mention that there is this is a main issue for inverse scattering. In inverse scattering, I'll give you the field outside, and I'll tell you to tell me the source JRT inside, and you won't be able to. And this is something important in this inverse scattering problems. Okay, let me see. What else? Oh yeah, there is the one that long one. All right, let me see. From Dimitri. About the previous question, answer please the end of okay. You told me that A and B was only contribution on the shell, yes. But when we expand the Bessel functions with the Taylor series, we will have contributions out of the shell, yes. Can we somehow force that non-shell contributions to be zero? Because the contribution from the next term of the Taylor expansions will always cancel it? Wow. I don't know. We have to think about this a bit. I suspect the answer is no, okay? I don't know if you can find some examples. I think I understand what you mean, Dimitri. But at the end of the day, yeah, with a delta functions, yeah, okay, that you have to be careful with. All right, tentative answer, no. If I think about it, I will write somewhere my thoughts, but I don't think you can do this, okay? Because it always cancels from the other term. Well, that's, I'm not sure if there would be a proof to show exactly that it's impossible, but I suspect there should be. Maybe not easy to get to. I think we finished with the questions.
Can I ask just one fast one? Yes. So basically, you mentioned the possibility to realize chiral photons. So is it actually possible for a light emitter to emit only chiral photons? And is this somehow related to the structural chirality of the molecule itself?
So, all right. Yes, you can do that, okay? And there is, yes, related to the structural chirality. I don't have any picture here. So, for example, one object that will do that is, let's say, a perfectly conducting helix, all right, where the pitch and the radius are in a very definite relationship. That this is actually, you can find this in a paper. I can try. Okay, hold on a second. Maybe just hold on 1 second. Maybe I can actually show you the paper. Then that helix will have an identical electric and magnetic dipoles with the right phase. Depending on the handedness of the helix, it will be left or right. And when you excite that helix, it will only produce a purely chiral photon. Yes, I have it here.
Okay, but this is we're still talking about your reduced definition of chirality, right? Using magnetic and electric dipoles.
Yes.
Yeah, okay. I was mostly talking about a molecule,
Okay.
a light emitter.
If you have a molecule, you're going to have to, I don't know of a molecule that will be equivalent to such electric and magnetic dipole equality. Typically, this doesn't happen.
Okay.
Yeah, so it's not, You might, I think it's not impossible because people now can make molecules that, synthesize molecules that are very weird in shape. The answer to your follow-up comment is yes, it will have to do with the chirality of the, so a chiral molecule will produce some imbalance on the plus and minus, but it won't be pure. It will be a little bit more of plus than minus, but it won't be. One of the components won't be zero, which is what you actually asking, and you will have to synthesize a very particular molecule if it's possible for you to do that. You have to work hard on that one.
Okay, and what about? Okay, sorry, I will just hold my questions. Thank you very much.
Sure.
We are out of time. We are 10 minutes already out of time. But thank you very much once again for the lectures. They were very interesting. And we will see you again after the pause, after lunch pause. So in the practice. Okay, thank you all, guys. Goodbye.
Bye.